All right, everybody, welcome back. Here is video number 2 for our unit on there. This is going to get a little bit more nitty gritty about dealing with simple harmonic motion. Specifically, this is the math part of this particular chapter. And it has to do with quantifying the behavior of the two classic examples of simple harmonic motion, which are the action motion of springs and things that are hung by springs, and then pendula or pendulums, if you wish, and how they swing back and forth. So a couple of things to kind of keep in mind in here. Again, there's going to be a couple of little math formulas that you'll end up using, and a lot of the homework, the mathy homework, is based directly on this kind of stuff. I think this is actually technically part of the homework part 1, but it was in video part 2, whatever. Anyway, they get too long anyway, so I have to split them up. So again, just to keep in mind of what this is. So first thing is, what's a wave? Wave is something that carries energy. There is some sort of a disturbance in the force, so to speak, that has caused something to move. Something has done work on an object, and then it's either swinging back and forth or it's bouncing up and down. But we've got some forces that are involved. There's like an applied force that maybe did the work in the first place, and then you've got some different sorts of restoring forces that are trying to pull that thing kind of back to where it started. So there's a couple of terms that I want to make sure that we're really clear on. I'm going to kind of move my picture out of the way here a little bit. Number one, there's a phrase that you hear a lot, which is called the equilibrium position. I want to make sure we're clear on what that is. Equilibrium position is if the thing was left to its own devices. In other words, there was no disturbing force. No work was done on the system. What would it look like? So with a pendulum, the equilibrium position of the pendulum would be position B here, basically straight down at rest. When you're talking about a spring, that can be a little bit harder to tell sometimes where the equilibrium position is. So for example, here, if you've got a weight on it, it's sort of partially stretched. It's not all the way down at the bottom, but it's not all the way compressed. So the equilibrium position is kind of like, where would that object sort of hang based on just its weight alone? If you're talking about a horizontal spring, something like that moving side to side, again, you're talking about sort of wherever that initial position is, when the spring hasn't been compressed, but it hasn't been stretched either. That's what we would call the equilibrium position. And again, in order to get something out of the equilibrium position, that's where that energy piece has to come in, that there's some sort of work being done on that system to disturb it, to get those things moving out of the way. And all sorts of simple harmonic motion are about energy transformations. We're always converting from, at the simplest, at least, potential energy into kinetic energy and then back into potential energy. There's lots of more complicated versions of this. It's where our spherical chicken's hanging out over here as well. There's lots of more complicated versions of these that get much more into detail about the exact types of kinetic and potential energy, and is there motion that's being lost in terms of friction, and is there all kinds of other things happening. But no matter what, you did some work. You've stored some work in that system. It's a type of potential energy. And then that system sort of fights back and then turns it back into some other sort of kinetic energy. So when you're talking about, say, a pendulum, you've got kind of maximum potential energy at the top. It's swinging through to kinetic energy down at the bottom, and then it's kind of coasting back up to the other side where you're going to get more potential energy, and it sort of repeats. When you're talking about a spring or something along those lines, you've got its equilibrium position. If you pull it downwards, you now have done some work against the spring. In this case, you're sort of helping gravity a little bit, but now you're doing work against the tension in the spring, and then it's going to be bouncing back upwards, and that's going to be sort of working against gravity, but then it's going to be converting it in compression, a different type of elastic potential energy that's up there versus the tension sort of elastic potential energy that's in there. So again, it's always about energy transformations when we're doing simple harmonic motion between these two things. So with this one, I want to take a moment and remember, or sort of remind you, that a lot of times when we're talking about the motion of a pendulum or the motion of an object on a spring, we're still going to use our traditional sine wave format, the typical kind of wavy format, because it's a lot easier in the sine wave format for us to kind of draw a lot of parallels between, say, a pendulum's motion and other types of motion that are out there, like the motion of light, or the wave nature of light, or the wave nature of sound. If we keep this sine wave idea underneath ourselves. So with this, a lot of times what's done is that concept of representing it in terms of position. So what you'll have is there's always an equilibrium position. So if you take a look at the equilibrium position in the pendulum, it's D in this particular spot, straight down, right? And then if you take a look in the graph, there's always a midline in here, and you can kind of see where I'm tracing across with my cursor kind of right there, or you can see it more easily down in this bottom one, but there's always sort of a midline that's in this. It doesn't necessarily represent where the equilibrium spot is, but there's always sort of a midline to it. So with position up in here, that would be the equilibrium position, that A would be maximum disturbance to, well, I guess, this side, if you look at the video to it. And then D, which is in the middle, is straight down. And then, if I can go the same direction as the picture is, G would be the maximum negative displacement, if you want to think of it that way. So you go positive and then to negative, and that's when it kind of swings back and forth between the two. Goes to the A position through D, and then back to G, and then back to A. So when we're talking about things like frequency, and we're talking about period, we're always talking about a complete cycle. So if we're talking about on this particular thing, a complete cycle would be through A, all the way through G, and then back up to A again, a full cycle, and out and back, so to speak. You could also say it's from D through D and then through D again. You've got to go through the full kind of range of motion, complete up, down, and back up again sort of idea. With velocity, by the way, again, the velocity graph's a little bit harder to interpret because, again, velocity would be zero velocity, would be up at this spot. And so that'd be zero, but going in the negative direction. So it's going this way, or I guess this way in my picture. And it would be having maximum negative velocity at spot D, sweeping through there. And then at G, it's got zero because, again, it's at the far side. And now it's switching directions, and now it's going forwards again. So it's going in the positive direction through D, where it's got maximum speed, and then it gets all the way to the far side at A. So again, velocity graphs are a lot harder for us to think about. I tend to think about them as more as position graphs. My spherical chicken is in here to remind me that this would be an infinite pendulum, right? One that's never slowing down. It's keep going, where it's maximum all the way, maximum all the other way, and there's no friction, no air resistance. The string doesn't have any mass. There's no fight against it. You guys know in a real sense that this true thing would get smaller over time and eventually reach equilibrium because of our spherical chicken assumptions that are in there. Okay, so when we're trying to actually quantify how a thing is moving, how a pendulum is moving, there is an equation for it. A couple, it's a kind of complicated looking. I'll move my picture here out of the way in just a second. Number one, again, definition here is what the term period means. So the word period here means time for one full swing. So again, that is an out and back, and that's an important thing to make sure that we've got in there. Hold on, let me get my pen going to something that makes sense. So when we're talking about the term period here, come on. Period here, we're talking about the time for one full swing. So from one side all the way through the other side and then back again. The symbol for period is T, capital T. This is in seconds. And then this is frequency, which is how often it's occurring. So frequency here is represented by a lowercase f, or when we talk about light, it's sometimes represented by one of these funky Greek letters. We'll come back and visit that later. So if this is in seconds, period is in seconds, that means frequency is in 1/seconds, also known as a per second. It's kind of a weird name for that. So again, that's that particular way that it looks. So when we take a look at pendula and trying to represent how they look, here is the crazy equation. Ta-da! Looks kind of crazy. Period is equal to 2 pi times the square root of L over G. Well, what in the hell does that mean? Let's take a look at this thing over here. I'm going to go click over to a video here. We'll take a look at it, and we'll talk about why would there be a pi in this thing. You guys can start to think about those. You guys have math before. The letter pi is always in the number pi, is always associated with a particular geographic object. So let's take a look at this pendulum wave. It's kind of cool how this thing works. So this is a set of pendula. So take a look at what he's done here. He's got a bunch of billiard balls to it. And each billiard ball is strung by a different length string. And it's kind of mesmerizing to watch this. So I'm going to let this play. It's about a minute long. I love how it spontaneously reorganizes into different patterns. And now all of these patterns are pretty much just optical illusions. Okay, so it's like cuts off suddenly. I know I hate that part too, but so what is causing this particular set of events? So let's take a look back at our equation over here. Why would it behave like that? Well, the sequence is here what these particular things relate to. So 2 pi, as you probably remember, is related to, pi is always related to circles, right? And the reason why it's a circle is because a pendulum is actually swinging through part of an arc of circular motion because it's tied by a radius string, and that ball can only move through that radius. So that's where the 2 pi comes into play, and it's related to the way that it's moving and curving through that circular motion. The second part that's involved with this is the L and the G. So the L is simply the length of the string. The longer the string, the slower it tends to move, the longer the period. And I'm going to kind of move my picture out of the way here so we can kind of see what this looks like. Let me get that out of the way. Sorry, that's kind of, I can't put it, I'll put it up here. So you can see this orange one that's in the front of this picture right here is got the longest string to it. And there way in the back here is a little red one or black one or whatever color that is back there. And it's got the shortest string. So these ones that are closest to us tend to move the slowest. The longest string tends to go with the longest period. In other words, the longest amount of time to go back and forth. And these ones at the back have just shorter strings to them, so they tend to move a little bit quicker. So the L part is simply the length of the string to it. And then the G at the bottom is simply gravity. The amount of gravity, the amount of force, and again, remember I talked about the restoring forces that are associated with this, is a major part of how fast overall these swing. So a pendulum is going to swing at a different rate depending on what planet it's on or how much gravity it's being associated with. So for us, typically G here is our acceleration due to gravity, 9.81 meters per second squared. And then L is just a length in meters of the string. And so all of this stuff where these things are going through these cool patterns is because each one of these has got just a slightly different longer string, which means they have a slightly different longer period, and you get these kind of cool resonance type effects almost. And again, it's sort of an optical illusion when they sort of come into these different patterns where they tend to overlap. So this is the equation right here, 2 pi times the square root of L over G has to do with the whole idea about what's the period and being able to predict the period of any particular wave. So there you go. If you want to look at some pendulum wave effect, it's kind of fun. There's another one. This one down here with the 7 in it is a cool one that does glow in the dark, has a great, drop the beat kind of thing to it. But this one's a little bit easier to see. So the equation for pendulum motion, T equals 2 pi, square root of L over G. Be really careful with your algebra when you're trying to solve for this thing. Move the 2 pi over first, then square everything. Be careful with your PEMDAS when you're trying to solve for this one. All right. When we're trying to represent this thing, again, graphically, I'm going to kind of switch gears towards moving to a spring as opposed to moving towards a pendulum. Different equations for springs than pendula. The lab that you've got to do, by the way, I should go back. The lab activity that I've got you guys to do, the lab simulation, has to do with playing with these different components of how a pendulum works, and can you predict whether or not what the length of a pendulum would be, or the effective mass and things like that would have on there. It's one of the interesting things about this is that mass is not in this equation. So you'll see it when you go play with that lab sim. All right, so for this one, talking about springs now and how things bounce around on springs. Once again, we're going to take a look at that sine wave form is a key part of interpreting or representing graphically how these things work. Again, we've got our equation over here of period is still equal to 1 over frequency. Those are the same thing. And again, it's a little bit easier to see how this particular graph kind of shows where period is the time that it takes to go from left to right, from crest through trough, all the way through crest again. Spherical chicken assumptions in here is that we're going to have the same amplitude up as we do down, that there's no loss in energy as this thing is bouncing, and that amplitude would stay constant over time. Again, real world situation, that amplitude gets smaller on every single bounce as you progress through time. But again, you can see that same kind of sine wave motion on these particular spring ones. So with these, there's 2 different equations that you need to be able to use with spring motion, and both of these are important in quantifying how springs work. So the first one is up at the top here, and you can see it's called Hooke's law. This is named after a dude. The dude's name was Hooke. It's not Hookie, it's just Hooke. But Hooke's law is listed up at the top here. Hooke's law determines how quickly something bounces or how much energy it takes. Now, you know this from your behavior right here, from your actions that you've done. I would like you to think about hanging weights from 2 different types of rubber bands, a real thick, fat rubber band and a little skinny rubber band. That you know that if you've got a rubber band hanging there and you hang weights on it, that rubber band is going to get longer each time. But you know that the amount of weight that can be supported by the rubber band kind of depends on the rubber band. So that's what this first equation is about Hooke's law. And so you can kind of see what this kind of equation is, that you're kind of adding particular weights to it. And what this thing is talking about is the relationship between force, how much weight is on there. Remember, force is Fg, how much weight is being involved in there, that if you add more force to it, that you're going to get more stretch to it. And that's what the X component of this thing is. The X in here is displacement of the spring or stretch of the spring. It can also be compression of the spring. So you guys know that if you're trying to make like a big car spring go closer together, it doesn't want to do that either. We typically think of them as being stretching out. But again, X here is about the stretch. Technically, it's actually about displacement. That's why they use the X for it, but it's the amount of stretch or compression of a spring. Then you've got this particular thing, which is K. And you can see it's over here, it's listed. K is the spring constant. K has to do with how stretchy the spring is or how fighty the spring is. So if you've got a really skinny rubber band, it's going to have a really low value for K. If you've got a real thick rubber band, that would have a real big value for K. If you think about springs, the little spring that's in your ballpoint pen has a relatively small value for K, but the big coil spring that's in your car, part of your shock absorber, would have a huge value of K. It's very hard to compress it and very hard to stretch it. The other thing that's in here is this, where you've got a negative sign. So here's the reason why the negative sign is in here. The motion of stretch is opposite the direction of the force in the spring. And that's why you've got the negative. It's a directional. Because if stretch is going this way, the force in the spring is going to be this direction. And so that's where the negative sign comes from. It has to do with the fact that it's a restoring force versus the work force that's being done. So again, that's why there's those two things on here. So if you're stretching it to the right, the force in the spring is to the left. Or if you're pulling it down, like in this particular case right here, if the force is due to gravity is downwards, then the tension that's in the spring is actually upwards. So that's where the negative sign comes from in Hooke's law. So again, imagine that you're hanging weights in there, that it's getting longer every single time to it. And then I've got an example of what this looks like. If you represent this graphically, more graphs on the next page, you can kind of see that in general, that should be a linear relationship, that you've got tension or stretch is on the x-axis, you've got force is on the y-axis right here, that for the more force that you add, the more stretch that you should get, or vice versa, the more stretch that you put on it, the more force that it's going to fight you. Now, Spherical Chicken says, you guys know with a rubber band that if you stretch it too far, it will eventually break. Or with a metal spring, if you pull it too far, it'll eventually distort. It'll just bend out of place. So this linear relationship is only over a very kind of narrow range of X values, of stretch values. But what's kind of nice about this is that with an equation like that, right here, you can kind of see it, that the slope of this thing is important. SLOPE equals K. Again, the nice thing about a graph like this is that if you think about what rise over run is, if we've got force over X, it equals K. Take a look at your equation right here and solve it for K. So if you move this over, you get what your value of K is depending on how you define what your F and your X are. That's why we don't worry about the negative sign in here quite so much. But again, the slope of that line of a force times extension graph is going to be the stretch constant or the spring constant that you've got. So here's a little bit more into that, kind of taking a look at this graph one more time. I'm almost done with my little presentation here. In terms of this, I'm going to move me up to the top. There I am. That when you've got a graph of this particular bit, that this bottom part down here is the stretch, if we're using Hooke's law, and that this part over here is the force that's being applied on this particular side. Let me put my actual pen back on here. Here's F, and then here's X. Just like we did back in that first chapter, area under the graph is also kind of a useful piece for us. So we know that the slope is rise over run, and in this particular case, if we calculate that, F over X equals K, that the slope of one of these graphs, the slope of a Hooke's law graph, is known as the spring constant. But what's kind of nice about this is that the area under the graph actually means something here too. It's the amount of force that you had to do to get that on there, which is also known as work. And you can see that work is on here. But over here, I don't have work written. I don't know if you remember this from the last chapter, but there's something called the work kinetic energy theorem, that when you do work on an object, you can store that work in the form of kinetic energy. So we actually get kinetic energy of a spring, like how much energy can you get from the spring? And here's this funky looking equation, 1/2 kx squared. It looks a lot like another equation that we've seen, 1/2 mv squared, from the last particular chapter. And that had to do with kinetic energy of an object when it's moving, say in a crash. But in terms of how does that come out of this particular thing, the area of this particular triangle under here is actually kinetic energy. So if you think about what this is, we can use the 1/2 base times height, right? Well, this is, in this particular graph, 1/2, the base of this graph is X, because it's displacement. The height of this graph is force. Okay, well, that sounds lovely. Well, I can do a substitution. 1/2 of this, I'm going to use my equation right here, of x times kx. Kx gives you an equation. 1/2, if I can get it to actually do its thing, equals, come on, my friend, give me my pen back. Stop it. Equals 1/2, there it is, k times x squared. And then there's a negative sign in there. That's part of the directional that's on there. So that's where this kinetic energy equation comes from. So when you talk about the kinetic energy of a spring, it's the area under a Hooke's law graph. So the slope of a Hooke's law graph is K, or the spring constant. The area under the graph is kinetic energy, or the amount of work that is being done on the spring to stretch it that far. So it's kind of a cool kind of couple of equations that you can use to kind of calculate or to represent the energy that's happening in these particular things. So for the pendulum, you've got the equation of the period of a pendulum swing, how long it takes to swing back and forth. And then for springs and the simple harmonic motion in spring-based systems, you've got two equations. One is Hooke's law, which has to do with force and the spring constant. And then you have the second one, which has to do with energy or work, which has to do with 1/2 kx squared, which has to do, again, with how far the string has been stretched and how stretchy the spring is. And both of those will give you the idea of how much kinetic energy or how much work you can get from that particular system. So there you go. Those are the ways that I'll go back to my other one so you don't look at a blank page, the ways that we quantify simple harmonic motion in pendulum and spring systems. All right, there you go. I will see you in the next video. Have a good one, guys. Bye.